Here is a curve and a question: where is its lowest point? You can see the answer immediately because you are looking at the whole picture. A machine cannot. It gets no picture, only the ability to stand somewhere and measure something local. And yet watch, it finds the bottom anyway, one step at a time, with no idea what the curve looks like. That's gradient descent. It's how essentially every machine learning model on the earth is trained. And it's a reason a computer can fit a line, recognize a face, or write a sentence. All of it is some version of what you just watched. Work out which way is downhill, take a step, and repeat. The name has two words in it, and one of them is easy. Descent means going down. That part we have just seen. So what's gradient? A gradient is what you get when you take a derivative and allow more than one input. When a function depends on a single number, a single parameter, one of you contain, its slope is just a number. That's the derivative, f prime of x. But a real model has many parameters, millions of them, and then you can't describe its steepness with a single number because it depends which parameter you wiggle. So you work out one slope for each one and collect them into a list. That list is the gradient. So the gradient is not some new harder object, it's the derivative once for every parameter. Which is a good news because it means we don't have to start with a million parameters. If we genuinely understand what happens with one, we understand all of them. The machinery is identical, just repeat it. So that's what we are going to do. One parameter and the simplest curve there is f of x equals x squared. A parabola, one parameter, one lowest point sitting right at 0. About as simple as a function can get while still being worth anything. And remember, the constraint we are under, the machine doesn't get to look at this picture. All it can do is stand at some value of x and measure something local. So what local measurement could possibly tell it where the bottom is? The slope. And a slope is just a number, how much something goes up divided by how much it goes across. Here's a line that climbs 2 units for every 1 unit it moves across. So the rise is 2, the run is 1, and the slope is divided by 1 plus 2. It's rising. Here's one that goes nowhere, no rise at all. So 0 divided by 1, a slope of 0, flat. And here's one that drops 2 units for every 1 across. That's the important case. So look at what happens to the arithmetic. The run is still plus 1, but the rise is minus 2. Minus 2 divided by 1 is minus 2. The line falls and the slope comes out negative. Not by convention but because the rise itself was negative. So positive means going up, negative means going down, and bigger the number regardless of the sign, the steeper it is. But a curve does not have one slope. One parabola is steep on the left, almost flat in the middle, steep again on the right, so the question has to be sharper. What is the slope at a one particular point? Here's how that gets answered. Pick any point on the curve, this one. Now zoom in on it, keep zooming, watch what happens to the curve as we go. It flattens out. The bend gets gentle and gentler. Until at high enough magnification, you can't tell it from a straight line. And that straight line is the answer. It's the direction the curve is traveling at that point. Lay it over the curve and the two are the same thing. At least right here. Now pull back out and you can see what it actually is. A line that touches a parabola at a single point and pulls away from it everywhere else. That's called the tangent, and the slope of the tangent line is what we call the derivative. Now watch it move along the curve, steeply negative over the left, falling hard, flattening as we approach the middle, until at the bottom it is exactly 0, laying flat across the point we marked earlier, and then climbing positive of the right hand side, one number changing as we move, describing the tilt of the curve everywhere. For our parabola, the slope at any point is the derivative of our parabola, which is f prime of x equals 2x. You already know how to get there, so I won't elaborate with what matters, what these things tells us. So let's plot it. This yellow line isn't another curve to study, it's readout. At every x, its height is the slope of the blue curve at that same x. Two different quantities on one picture. Blue tells you how high the wall is, yellow tells you how tilted it is and which way. Take x equals 3, put it in, f prime of 3 is 6 on the blue curve. That's a tangent leaning uphill to the right, rising. On the yellow line, that same 6 shows up as a height 6 units above 0, and here's what it buys us. The slope is positive, which means moving right takes us higher. So to go down, we go left. Now x equals -2, the slope is -4, falling. The tangent leans the other way. The yellow line sits below 0 and the arrow flips. Downhill is to the right. And at x equals 0, the slope is exactly 0. The tangent is perfectly flat and the yellow line crosses the axis. That's the machine signals that it has arrived. It can recognize the bottom without ever seeing the whole curve. One more thing, and it's the part people skip. The magnitude matters too. At x equals 1, the slope is 2, gentle, and we are close to the bottom. At x equals 4, it's 8, steep, and we are far away. So this single number is doing double duty. Its science tells us which way to move, and its magnitude tells us roughly how far we have to go. So now we know the slope tells us which way to go. But why is it the opposite direction? Let's actually check that on both sides of the ball. Start on the right at x equals 3. The slope here is +6. The curve is rising and you can see exactly where that 6 comes from. Drop straight down to the yellow slope line and there it is, 6 units above the axis. Now suppose we subtract the slope from x. We are taking x and subtracting a +6. So x gets smaller. Smaller x means we move left. And left from here is downhill. That works. Now go over to the left wall at x equals -3. The slope here is -6. The curve is falling. And look at the yellow line on this side. It has crossed below the axis. That crossing is the sign flipping, and it's the entire reason what happens next is different. Subtract -6 from x and we are subtracting a negative number, which makes x bigger. Bigger x means we move right, and right from here is downhill too. That is the part worth pausing on. Subtract the slope sound like it should always push you leftward. But because the slope carries a sign, subtracting it flips direction automatically depending on which wall you are standing on. We never told it which way to go. The sign did that for us. Either side of the valley, subtracting the slope walks you downhill. So that's our rule. X becomes x minus f prime of x. Draw it from x equals 4. The slope there is 8. 4 minus 8 is -4. And we have shot clean past the bottom and landed just as high on the other side. The direction was right. The distance was absurd. That is because the slope size is measured in the units of function, not in the units of x. It is not a distance and there is no reason it should be a sensible one to travel. So we scale it down, multiply by a small number eta. Before we subtract, x becomes x minus eta times f prime of x. Eta is called the learning rate and it is our to choose. Now let's run it properly with eta at 0.1. We start at 4. The slope is 8, so we move minus 0.8, landing at 3.2. There the slope is 6.4, so we move minus 0.64, landing at 2.56. Again, slope 5.12, step minus 0.51. And again we just keep going. Watch the trail it leaves. The dots bunch up as it approaches because look at what the step sizes did. 0.8, then 0.64, then 0.51, then 0.41, 0.33. Every single step is smaller than the one before it. And you can see exactly why. Follow the yellow marker down on the slope line. As the ball settles toward the bottom, that marker slides down to 0. The slope is shrinking. And since every step is built from the slope, the steps shrink with it. Nothing in our code says to slow down. The algorithm decelerates into the answer all by itself. That run worked, but it worked because of a number I picked for you without explaining it. The eta, sitting in the middle of the octet. So let's go back to the top of the hill and look at that choice properly. Here we are again, standing at x equals 4. The bottom is down there at 0. We know which direction to move against the slope. We settled that. The question left is how far. Let's get the one number we need. Drop down to the slope line one last time. The derivation at 4 is 8. And notice this is not the thing we are choosing. The function hands it to us. And it stays 8 no matter what we decide to do next. So I will clear the slope line away because from here there is only one thing varying in this whole scene. And it is not the derivative. Our update is new x equals 4 minus eta times 8. Everything now depends on that eta. Try a small one. Eta of 0.01. 0.01 times 8 is 0.08. 4 minus 0.08 is 3.92. We move less than a tenth of a unit from 4 to 3.92. Barely moved at all. Now 8 of 0.1. 0.1 times 8 is 0.8. 4 minus 0.8 is 3.2. That is a real step, a noticeable move toward the bottom, but still comfortably on our side of the valley. And now 8 of 1.1. 1.1 times 8 is 8.8. 4 minus 8.8 is minus 4.8. Look at that number. We didn't just overshoot the bottom, we crossed the entire valley and came out the other side higher than we were started. Let's put those three on the curve so you can see them. Same starting point, same slope, three different landing spots, one that made real progress and one that flew clean past the target and ended up worse off. But a single step doesn't tell the whole story. What matters is what happens when you keep going. So let's run all three. The small one is doing the right thing, just barely. 18 steps in, it is at 2.78. Still a long way out. It will get there eventually, but eventually on a real model can mean hours of wasted compute. The middle one settles into the bottom. Big strides while the curve is steep, smaller ones as it flattens and it is arrived. And the large one doesn't recover. Every overshoot lands somewhere steeper, which produces a bigger step, which overshoots further. 18 steps in, X is over 100 and climbing. If you ever watched a training run turn into then this is what happened to it. Same starting point, same derivative, three completely different outcomes, and the only thing that changed was eta. So the learning rate is the choice you make, not something the math hands you. And there is no universally correct value. What counts as too big depends entirely on the shape of the function you happen to be working on. A step that is perfectly sensible on one problem will blow up on another. Now let's step back because there is something here we all learned long before any of this. A minimum is where the slope is 0. And look, our curve says exactly that. Down at the bottom, the tangent lies perfectly flat. And on the slope line, that is the moment it crosses axis. Flat tangent, slope of 0, same point. So we don't have to walk anywhere to find it. We can just ask where the derivative equals 0 and solve. F prime of x equals 0, 2x equals 0, so x equals 0. And there it is, exactly the spot we have spent the last few minutes carefully creeping toward. Exact instant one line of algebra and no walking downhill at all. Which raises a fair question, what were the last 10 minutes for? And the honest answer is that for this function, you would be completely right. Solving it directly is trivially easy, and gradient descent is a ridiculous way to do it. So why does the entire field run on the gradient descent instead? 3 reasons. And notice that from here on, I can't draw any of them. First, most equations have no formula for the answer. Take this function, its derivative is perfectly easy to write down, but setting it to 0 gives you an equation that no algebra in the world can solve for x. There is no formula. Not because we haven't found it, because it doesn't exist. And yet, evaluating that slope at a specific point, completely trivial, you just plug a number in. Second, real models don't have one parameter. Ours is a single unknown. So, setting the derivative to 0 gives one equation, and one equation is easy. A neural network has a loss depending on a million parameters. Setting the derivative to 0 means writing a million partial derivatives. Setting everyone to 0 and solving all of them simultaneously, nobody does that. It is not a matter of passion, it is not tractable. Third, even when a formula does exist, it can cost too much to use. In linear regression video, we made the normal equation which solves linear regression exactly. But look at that inverse. Inverting that matrix costs roughly n cubed operations. At 100 features, fine. At 100,000, hopeless. So here is where all of this lands. We almost never get to solve for the bottom, but we can always evaluate the slope where we are standing. And as we have seen, that is enough. It tells us which way to move and how far. Compute the slope, step against it, repeat 2 lines. So that is the whole algorithm that trains essentially every model in the world.